Thank you so much for watching this online video tutorial. Like, comment, and share, as well as subscribe to our channel at Good Better Best Online Videos for more video content. Right, grade 11s, we're looking at electrostatics. Okay, now which is a new topic, back to physics. We've just come out of finishing quantitative aspects of chemical change. Okay, so we're going to introduce the physics topic under the main topic of electricity and magnetism. Okay, and electrostatics will tie in straight into magnetism, which will tie in straight into electric circuits. Okay, so let's start with electrostatics. Now, there are two types of charges, okay, that we get and that we talk about especially, Okay, so what I was saying is that there are two types of charge, positive and negative, okay, that exist, okay, and electrostatics obviously encompasses both of those. Okay, we talk a lot about that. All right. The atom is electrically neutral. All right. When it loses electrons, it becomes more positively charged, and when it gains electrons, it becomes obviously negatively charged. All right, which is now no longer neutral. Objects do become charged when they are rubbed. So in other words, friction does cause electrons to be removed from one object and be transferred to another. For example, your ruler, all right, your ruler that is rubbed on your head. If you have a plastic ruler, if you just take your ruler and you just rub it very, very nice and hard on your hair, you know, just give it a nice little rub, whatever, and you put it on the page will lift up, will be attracted to the ruler. Okay, shows the difference between positive and negatively charged. So a negative charge attracted to a positive charge, or a positive charge attracted to a negative charge, that obviously means it is force, not force of attraction, but rather there's attractive force rather. Right? Obviously, same like a magnet, force of attraction. Okay, the North Pole is attracted to South Pole, etc., etc. South Pole is attracted to North Pole. Okay. Only insulators, substances which cannot conduct charge, can be charged by friction. Okay. Conductors, the charge leaks away over a period of time. So insulators, it cannot conduct charge very well. Can be charged by friction, so lots of rubbing. So that's why the ruler, you rub a lot, rub. Touch the piece of page, the page will lift up with the ruler. Okay, so obviously, again, two types of charge, positive and negative. Okay, you get force of attraction, right, and obviously force of repulsion. Okay, now let's have a look at another heading, which is called the force between charges. Alright. So objects exert forces on one another. Okay. When two objects have the same charge, they repel, and of course when they have opposite charges, they attract. And there was a guy by the name of Charles Coulomb. Okay, that's obviously not for examination purposes. Physics or physical sciences doesn't pride itself in asking history questions, but anyway, it's just for a little bit of history. Charles Coulomb, who lived in the late 1700s. Okay, late 1700s, long time ago. Okay, investigated the forces between charges. His findings state the following law, which is called, of course, Coulomb's law. Okay, and we need to take this down. Cool. Coulomb's law states that the attractive or repulsive force between 2 point charges is directly proportional okay, this word here, proportional to the product of the charges and, we're going to use the ampersand here, and inversely proportional to the, I might run out of space, to the square of the distance between them. Sorry, I have to make use of, I have to keep that label there, unfortunately, so obviously didn't care to think how close it was. So let me read that again for everybody so we can all understand. The attractive or repulsive force between 2 point charges is directly proportional to the product of the charges and inversely proportional to the square of the distance between them. Another way to say that is that the electrostatic force between 2 point charges, alright, which we know can either be attractive or they can be repulsive, alright, is directly proportional to the product of the charges and inversely proportional to the square or the distance between them squared. We can obviously rearrange some of those words to around using our English lingo. To still state a perfectly legitimate definition for Coulomb's law. Okay, so I'll give you guys some time to take that down. Alright, let's have a look at it in symbols. So basically we're saying that the force, electrostatic force, is directly proportional to the product of two charges, Q1 and Q2, and that same force is inversely proportional to the distance squared between the two charged objects. Therefore, we get a formula for Coulomb's law to say that the electrostatic force, alright, the force between the charges, is equal to Coulomb's constant, which is denoted by little k. Little k is equal to 9 times 10 to the 9 newtons per meter squared per Coulomb squared. Okay? Newtons per meter squared per Coulomb squared. That's Coulomb's constant. Add that here. Coulomb's constant times the product of the two charges, so Q1, Q2, charge on object 1 times charge on object 2, all over the distance squared between them. Okay. Q1, Q2, measured in coulombs. Okay. R is distance measured in meters. F is the electrostatic force measured in newtons. Okay. So called SI units. Okay. Hope that makes sense. Cool. So, shall we take a little bit of an example? Okay, just wait for you to get that down quickly. So let's say we have a little bit of an example here. We have two charged spheres. Okay, one has got a positive charge on it. Okay, we surely should know that little symbol by now. This little Greek U means it's pronounced mu. Mu. All right, and we've got positive 5 microcoulombs, and we have negative 3 micro coulombs, and the distance between the centers of the spheres, okay, I'm just going to say, obviously the centers from here there, the distance between them is about 0.6 meters. Okay, well, so how do we do this example? Well, F is equal to K Q1 Q2 all over R squared. So they want obviously to calculate F, so that's 9 times 10 to the 9 brackets, other brackets Q1, which is 5 times 10, a microcoulomb, a micro is times 10 to the negative 6. Notice even though charge 3 is a minus, you do not put the minus sign into the equation. It's just to show that they are that it is force of attraction and not repulsion. Okay, so you leave it as 3 times 10 to the negative 6. You do not add the signs when you are adding the values of Q1 and Q2 over 0.6 all squared. All right, if you have a look at that, I need my calculator. Should give us a relatively small answer, about 0.375, so 0.38 newtons if you round it up to 2 decimal places. All right, quite simple, quite easy. All right, very, very small force between the two. Okay, so that's just a little bit of an example there. What I think is appropriate now is we're just going to have a look at some more of those examples just here in the live class before we move on to electric fields and drawing them and doing formulae and how to calculate the strength of an electric field. Okay. All right, let's have a look at some of those questions. Okay, from the physical science textbook by J.M. Lucas on Coulomb's law, which was exercise 6.1, I think. Yeah, 6.1, not 1.6. Almost right, 1.6. Okay, 1.1. Two tiny spheres carrying charges of positive 4 microcoulombs and negative 3 microcoulombs are separated by a distance of 50 millimeters. Okay, so your information can go on as follows. Just rule a separate line here for the information, or maybe even a line just on this side. Q1 positive 4 mu c, Q2 negative 3 mu c, R equal to 50 millimeters, which is equal to, of course, 5 times 10 to the negative 3 meters, and we're going to add that into our formula here, which is calculate the magnitude of the force between the spheres, K Q1 Q2 over R squared. Okay, and that's going to equal following 9 times 10 to the 9, 4 times 10 to the negative 6, and 3 times 10 to the negative 6, all over 5. Sorry, not 5 times 10 to the negative 3. Sorry, made a bit of a mistake there. It's 50 times 10 to the negative 3. So that's 50 times 10 to the negative 3. In other words, so the comma was here 1, 2, 3. So that's 0.05. Yeah, just check. 50 divided by 1000. Yeah, 0.05. Yes, it is. Right. And therefore, the electrostatic force between the two spheres. Oh, sorry, I forgot to square it. Got to square that. The electrostatic force between the two spheres is 43,2. Just rounded off to one decimal place. 43,2 newtons. 1.2, is the force attractive or repulsive? Alright, well, we can definitely see we've got a positive force here in between, and one was positive and one was negative, so we definitely know that that is a force of attraction. Alright, or we could have written it and said attractive force. Right, 1.3, if the distance between the spheres is halved, how will this affect the magnitude of the force? Alright, so if distance is halved, alright, so R is now no longer just 1R, R is equal to now half R, right? Because this is R over 1, R divided by 2 would be half, right? Does that make sense to everyone, yes or no?
Yes.
Okay, cool. So now remember, distance is always squared in the formula. So therefore, if it's distance squared, all right, so it'll be a half r, all squared, which is basically equal to a quarter r squared. All right, it's equal to a quarter r squared. Okay, so they're asking, if the distance is halved, how will this affect the magnitude of the force? So our answer is that it would be 4 times greater. So let me explain how I derived at the 4 times greater part with a mathematical angle. So of course r, this is 1, a whole number, but now this becomes half r. Now in our formula we know that force is directly proportional to the product of the charges and inversely proportional to the distance squared. So r in the formula is now this value. So let's sub in. Okay, or let's rather working this out in multiple choice, you need to do it like this. So we have that over here. So we have Q1, Q2, all over half r squared, which obviously gives us still the top as normal, all over a quarter r squared. Now what number is invisible on top? There's a number invisible on top here. What would that be? It's number 1. We have a fraction, 1 over 4 multiplied by Q1 Q2 over r squared. Obviously we know where this comes from. This is obviously equal to the force, right, over here. So 1 divided by a quarter. What is 1 divided by a quarter? Anybody? 1 divided by a quarter? Seriously. Looking for an answer. Thank you, Nadima. 4. It's 4. So 4 times what the force is equal to, which is Q1, Q2 over r squared. So hence why our answer, therefore, which I'm going to put in green, therefore, the force will be 4F, 4 times greater. 4 times this, it means it's 4 times greater. Okay, i.e. 4 times greater. Alright, cool. So that was question 1. Before I mark any of the other questions, I'll maybe just check are there any problem areas, and then whatever problem areas that we wanted me to go through, I'll just go through those questions. Okay, 2.2 is the request. 2.2, just 2.1 was just calculate the force between there. Okay, and so we got an answer, should have got an answer there of 32,4 newtons of repulsion. 2.2, if the magnitude of each charge is now doubled, how will the magnitude of the force be affected? Okay, so again, the same thing mathematically. They ask us now, how will if the magnitude of each charge is doubled. So now Q1 and Q2 are now 2 times Q1 times 2 times Q2, right? So the formula, F is Q1 Q2 all over r squared, is now changed to, if I sub that in, for Q1 I have 2 times Q1 times 2Q2 all over r squared. Now obviously what do I have here? I have coefficients. Alright, so 2 times 2 gives me, so I'm going to have 4 over 1 times Q1 Q2 all over r squared, and obviously we know this is equal to F, the force, the electrostatic force. So 4 times that, therefore our answer for 2.2.2 is that if the charge of each is doubled, alright, on both spheres, if it's doubled, then therefore the force will be 4 times greater. Do you understand the mathematical reasons why? Silence. So I'm not sure if that's a good thing or bad thing.
I'm wanting to know, did you get the 4 in the third row for like 2 times 2?
Yes.
Okay, thanks.
Okay. Because remember, if just like algebra, if x had to double itself, it would be 2x, right? So we're using q now. So q was like, there was a 1 there, so you double it, it becomes 2q. So you got coefficients now, so 2 times 2 is 4. All right. Okay. Question 3 said that the electron and the proton of a hydrogen atom are separated by a distance of 35 picometers. Okay. So picometers, pm, it's times 10 to the negative 12 meters. Okay. A decameter, I think, is times 10 to the negative 10. Okay, but we'll work on this for now. I'll confirm that a little later, or shortly, should I say. Calculate the force between them. So F is still equal to Q1. Let me add in my Coulomb's constant first. Okay, Q1, Q2 all over R squared. Okay, 9 times 10 to the 9. Okay, so we know the charge on a proton and electron are the same numerical value, just the signs have changed. So it's basically 1,6 times 10 to the negative 19 times another 1.6 times 10 to the negative 19. So that's just, I'm just going to put them squared because it's the same value. So I'm going to just say squared. And they're 35 picometers apart, so that's 35 times 10 to the negative 12 squared. Okay. And we add that all in on our calculator. Should get an answer of 1,88. I'll round it off because 1,8808. So to 2 decimal places, 1,88 times 10 to the power of 10 to the negative 7. All right. And that is newtons. And that is an attractive force. So add in attraction for question 3. Okay. There was a question also for question 4. 4.1. So question 4, 2 alpha particles are separated by a distance of 10 to the negative 10 meters. 4.1, calculate the force between the particles. So again, F is equal to K Q1 Q2 all over R squared. Okay. Calculate the force between these two particles. So let me just check something quickly. If they are alpha particles, 2 alpha particles, calculate the force between them. So alpha particle is 2 times that of the value of a proton. Alright, so it is basically, if you enter in that, and that information was supplied in the exercise we sent out actually. Alpha particle is 2 protons or 2 neutrons, so 2 times the positive value. Okay, so that is going to be 9 times 10 to the power of 9 Coulomb's constant times 2 times 1,6 times 10 to the negative 19, and it's the same value because there's 2 alpha particles, so I'm going to square them instead of writing it out again. Otherwise you write it out like this. Let me just do it one time for everybody. 2 times 1,6 times 10 to the negative 19. Alright, and it's 10 times 10 to the, sorry, it's just 10 to the negative 10 meters. It's very small, very close to each other. Alright, so we just square that. Okay, if we plug that in on our calculator, we should get an answer of about 9.22 rounded off times 10 to the negative 8, and that is newtons, and that is repulsion. You know why? Because they are both positive values. Alpha particles are positive values, okay, not negative values. One is not negative and one is not positive. Okay, and that was 4.1. 4.2 asks, if one of the alpha particles is replaced by a proton, how would this affect the magnitude of the force? Okay, well, it's very simple. We don't even need to do a calculation for this. All right. If one of the, since a proton, the value on a proton is equal to half of an alpha particle, okay? Because an alpha particle, as it says, is 2 times the value of a proton. So 2 times 1,6 times 10 to the negative 19. So a proton is half that of an alpha particle. So half of this would just be this value. So if one of the values is halved, and no longer 2 times 1.6 to the negative 19, I take 1 out and I have a proton times an alpha particle. I've surely have I halved I've halved the force. So therefore the force will be halved. And I'll explain it by going back to another example. So I think it's here. No. So here we see where we see in question 2.2 the magnitude of each charge is now doubled. This is basically the alpha particle, 2 times that the charge on a proton. So obviously if it's 2 times that of the charge of a proton, obviously it's going to be 4 times greater. So now let's say I take this alpha particle away. So if I take 2 times Q2 out and I just replace it with Q2, obviously I'm not going to have 2 times 2, I'm going to have just 2 on top here, and 2 is half of 4. Hence why when we come back here to our let me just take this other layer out, sorry. Come back here. If I obviously half this, I get just a proton. So a proton times the alpha particle is going to be half. So here, therefore, the force will be halved. Do you understand the explanation? Okay.
Referring to the question.
Sure, I'll re-explain. So an alpha is 2 times that of a proton. A proton is half that of an alpha particle. So if I just, okay, let me just not be lazy. So if I have an alpha particle which is 2Q1, and I take Q2 and I just have just Q2, so it's just 1, it's not double. Okay, so if I take that and I say, well, F is equal to 2Q2 or 2Q2 times Q1 or 2Q1 times Q2, let me just fix that. 2Q1 times Q2 all over R squared. I'm going to end up with just on top 2Q1 Q2 over R squared. So 2 over 1 over here multiplied by Q1 Q2 times R squared. So my force factor here is only going to be 2 and not 4, because an alpha particle is double that. So there I would have had 4 had Q2 being an alpha particle, but Q2 is just a proton now. So it's just half. It's no longer 4 times greater, but it's half of that, so it's 2. So in other words, the force is therefore halved now. Is that cool? I want to move on to electric field strength quickly. Okay, or what an electric field is. So let's just give another hit. Let's try yellow. Okay, electric fields. Okay, so electric fields. What is it? Electric field, first of all, this is the space around an electrical charge. Alright, just get that words in. In which, I always never know how to spell which, in which any other charge will experience a force which is electrical in nature. Alright, there you go. Okay, space around electrical charge where any charge will experience a force which is electrical in nature. We're going to move on. Then we'll come and open up the topic of electric field strength, because there is a strength that can be calculated in electric field. Sometimes could be a strong one, could be a weak one. We don't know. Okay, electric field strength. Okay, what this is. Okay, I'm going to use another color for it as well. All right, at a point in the electric field, or in the field. Okay, at a point in the field, okay, what electric field strength is? It is the force which a unit of positive charge experiences at a point. Electric field strength at a point in the field is the force which a unit of positive charge experiences at that point. So it should be that point. So it'll be add TH and T. At that point. Which is defined by the following formula. E is equal to F divided by, some textbooks give it as little q. Others give it as F divided by capital Q. Fact is, it must be charged at the bottom. Okay, so E is the electric field strength, okay, and E is measured in newtons per coulomb. As we can see, force is measured in newtons and coulombs is measured in coulombs. I mean, charge is measured in coulombs, where force is the force of the charge, and Q is the magnitude of the charge. Electric field is a vector quantity. It does have magnitude and direction, okay, and it will have the same direction as the direction of the force experienced by the positive test charge at that point. All right. Then there's also field strength that happens at a particular distance. Okay. And all right. This is an electric field, which we'll just dub field. Field strength at a distance R, which is the symbol for distance in this section, from charge Q. Okay, so let's say we have a charge sphere Q over there, or let's make the sphere a different color. Okay, and here we have, this is R, and we want to know at this point here what is the electric field. Okay, that formula would be E is equal to Coulomb's constant times the charge all over distance squared. Very similar to the what's the word I'm talking for? What's the word I'm looking for? Very similar to the Coulomb's law formula. Okay, so Q is still charge measured in coulombs. E is still the electric field strength. R is still the distance squared between, or R is the distance between Q and the point at which E is calculated. So it's still measured in meters. So the formula applies to radial fields and not uniform fields. Okay, and these formulas that they do apply to those radial fields, which I will demonstrate a little bit next week. All right, what they are. Okay, I'm just going to get my phone again. I'll take a photo, and then we've got 3 questions to do, and that'll be the end of our session for this evening on electric field strength, which is quite basic. and then we'll have a look at these questions in the exam. And that leaves us for where we are tonight, grade 11s. Okay, we'll come back, we'll have a look at some more intricate questions of electrostatics before moving on to electric circuits.